Welcome to the third lecture on tectonics and geodynamics. So, this would be the third of this course. This time we are going to be talking about the nature of the sea floor. Now, before this, the main topic that the concept we'll deal with here, we'll be talking about the nature of the sea floor. Is the sea floor static or is it dynamic? And all of these observations, the debate about what the nature of the sea floor is, ultimately this will evolve into events and observations that ultimately led to the evolution of the theory of plate tectonics. So, what we'll do is to start off from here, but with a little bit of a flashback. Now, at the end of lecture number 2, we'd discussed the continental drift theory, all the evidence that existed in favor of continental drift theory, but finally there were some major objections, particularly to do with the nature of the mechanism by which continental drift operated. Because of that inability, the theory of continental drift, it had fallen out of favor by the end of the 1930s. So now it needed something extra. The problem, of course, was, although it had fallen out of favor, a new theory after the Second World War would actually bring it all back, and continental drift theory, the truth of it, would actually come out in full splendor through this theory that we now refer to as the theory of plate tectonics. Now, we must begin with what continental drift actually talked about. Continental drift actually assumed that there were sialic continents. So, these continents were made up of predominantly silicon and aluminum, less dense materials that were floating on top of a denser ocean, which was dominated by silicon and magnesium bearing rocks. So, it's referred to as the seamatic layer. So, the continental drift theory really assumed that sialic continents were moving on top of seamatic oceans. This was the nature of the plate tectonic theory. The whole premise, therefore, was that the continents were moving and the seafloor was static. So, that is where the whole debate actually rested up to the end of the Second World War. The problem, of course, was we need to know what the seafloor is actually like. And it's important to know that, because the seafloor is a part that's hidden from us because of all the water that covers the seafloor. Incidentally, it's even true at the present time. We actually know more about the surface of Mars, the surface of Moon, than we know about the seafloor of Earth. It's so well hidden and it is so difficult to explore that accessibility to information on the seafloor is actually limited even compared to those on other planets. So, let's just go back in time. What was known about the seafloor at the time the continental drift theory was proposed? So, the earlier notion of the seafloor was mainly to do with the topography of the seafloor. So, a scientific expedition, the first real scientific expedition sent out to actually try and gain scientific information about the seafloor, was called the HMS Challenger expedition. It was a British expedition and it was carried out in the period 1872 to 1876. Now, in the course of many things, it discovered 4,000 different species of fauna and flora, but more importantly for our purposes, it did discover that there was a part of the Pacific Ocean which is now referred to as the Challenger Deep. There, the Pacific Ocean was greater than 8 kilometers below mean sea level. So, the sea floor itself was very, very deep. It was much greater than the usual depth of around 4 kilometers that most of the sea floor was supposed to have. Now, what this actually revealed for the first time is that the ocean floor was not a monotonous flat entity. Now, as more and more investigation on the seafloor happened, the First World War also was a part during which some more information was collected by people. But the first major scientific notion that was actually discovered on the seafloor was by a person called Johnston. In 1923, he recognized that there were long, deep, narrow gashes on the ocean floor. Now, he published this in 1923 and the First World War had ended in 1919. Now, in the First World War, one of the major modes of fighting was actually to dig trenches at the front line, and the soldiers would actually hide in those trenches and shoot at the enemy soldiers who were in trenches just across a short distance across. So, trenches were actually these long, deep, narrow gashes that were shoveled into the top of the surface. So, when people noticed these long, deep, narrow gashes on the ocean floor, Johnston almost automatically referred to them as trenches. So these long, deep, narrow gashes on the ocean floor, from then on, these have been referred to as trenches. So ocean trenches were discovered as long back as 1923. So it's over 100 years back. Now later on in 1951, when expeditions, again began to look in detail at the ocean bottom, the Challenger Deep was actually found to be a part of one such trench. Now this trench is what is now famous as the Mariana Trench. So the Challenger Deep was actually the southern end of the Mariana Trench, and it wasn't even the deepest part. The deepest part is more than 10 kilometers below mean sea level. Now in the 1920s and 30s, a geophysicist by the name of Henning Meynes, he actually made gravity measurements, and he could identify that these trenches, these long, deep, narrow trenches, these were places where the Earth's crust was actually going down. These were areas of downwelling, we call them, of the Earth's crust. So that meant that there was a negative mass balance right in the column which below the trenches. So there was an absence, there was a mass deficit. So this is where more or less the knowledge about the seafloor topography or the seafloor stood till the Second World War began. However, there was one additional technological advancement which had given us some clues about the seafloor, and this had to do with the discovery of a mode of communication which was at that time revolutionary. It was called the telegraph. Now many of the students of today, you who are listening, most likely listening to this, would not even have heard of the telegraph, but this was one of the fastest modes of transmission, right, that existed even at the time that we were children. So it's in the 1960s, 50s, the 1970s, right? These were the main modes of rapid communication. Now at that time, there were two sets of scientists. One was William Cooke and Charles Wheatstone in England, and Samuel Morse, famous for the Morse code, Leonard Gale and Alfred Vail in the USA. They invented something called the telegraph. This was in the 1830s and 1840s, right? Long before much knowledge about transmission of communication by wireless was known. Now the first transatlantic telegraph line, this was laid down in 1858, but almost immediately afterwards, within 3 weeks, something disrupted the line. So people had to try to lay it again, because people were needed to rapidly communicate between trade in America and London, which was actually one of the most important places on earth at the time. So once this line was set up, it became operational by 1866, and it was functional till by the 1920s. There were at least 12 transatlantic telegraph lines between Europe and North America. So these were now the major modes of rapid communication of information. Now in 1929, precisely on November 18th, there was an underwater earthquake. So seismometers at the time could actually record, and they knew that this was inside the oceans. So one could detect that at a depth of over 3,000 meters, there was an underwater earthquake, and because of that, all 12 telegraph lines, they were disrupted. The disruption was in 28 different places, and that completely disrupted communication between Europe and North America for quite some time. Now, though people tried to repair it, no one really knew why this earthquake had disrupted the cable lines. What did the earthquake actually do that caused disruption of the cable lines, and where did these earthquakes occur? So what people did realize, that they knew that it was an earthquake which had caused this, and because the earthquake had caused this disruption somehow, it was important for us then to understand what the seafloor topography was like, and it was important also to identify the epicenters of these underwater earthquakes. Where were these earthquakes? Because somehow it was understood that these earthquakes could cause this kind of disruption. So then people had wondered about it, but then there was this major event in human history because of which science had to wait. So from 1939 to 1945, the Second World War really put a stop to all proper science. Now, it stopped science communication, limited science publications, but it didn't actually limit scientific discoveries, because many of the technological advancements that happened during the Second World War, they actually were instrumental in giving us all this knowledge in the post-war period. So at this time, right, immediately after the war, it was then realized there was a project given to what's called the Lamont Doherty Institute in linked to Columbia University in the USA. And there, a person called Bruce Heezen, he actually worked with the most important person in the lab, whose name was Morris Ewing. And in 1952, they demonstrated that there was an underwater landslide which had actually been dislodged by the earthquakes. And this happened really off the coast of Newfoundland, which is the northern part of Canada. So as you can see, this is the continental shelf. So this was the continental shelf. So from the continental shelf, as you go down, right, sediments were deposited on the continental shelf. There were sediments on the continental slope, and this was the abyssal depth. Now, what the earthquake had done is that it shook the sediments out here, and it dislodged sediments from this part, and the sediment body began to move down very, very, very fast. It moved down on the scale of hours, right, and it could travel over distances of 1,000 kilometers. So 1,000 kilometers within an hour, and it would carry all these sediments that had collected on the shelf and on the slopes, and it would carry it very, very rapidly, right, and deposit it in the deep sea. Now, this huge mass of water was really a debris flow. It was massive. It was traveled very, very fast, and it was such a huge mass that this was what actually caused disruption of the cable lines. So now, Bruce Heezen and Morris Ewing demonstrated that it was this kind of underwater landslide, which they referred to as a turbidity current, because this huge mass of sediment laden water, it was extremely turbid, and this became popularly known as turbidity currents, and we now know them as a very, very important phenomenon in geology, and especially under the sea. It's one of the most important things that controls sediment transport inside the deep sea. So this underwater landslide, this had been triggered by an earthquake, and this created a turbidity current, and this turbidity current was what disrupted the cables. Now, this was then understood, then the cause, these studies, this project that had been given to Heezen and Ewing, it actually managed to tell us, right, what had disrupted the cables. But more importantly, people realized that if you had to understand why these things were happening, and if you had to use the seafloor, right, for different types of communication, then you had to understand what the seafloor was like. And because of that, a lot of money was poured into research which was actually dedicated to seismic refraction studies on the seafloor. And this was done to find out, majorly to find out where major earthquakes actually took place in the oceans. Now, these studies, automatically, when you had to do these studies, it provided information both about the surface of the seafloor itself, what the topography was, and also about the underwater structure. We won't talk about much of that right now, but we'll talk more about the topography and what it actually told us. Now, during the Second World War, this technique called sonar, right, it was actually sound waves which were reflected off the seafloor. This was used extensively to profile the seafloor. It was used for submarines, etc., that were used in the war. So a huge amount of data was collected. And at that time, that information was not published for obvious reasons. It was sensitive. But following that, in 1952, again, from the Lamont Doherty Research Institute, this is this famous laboratory, Marie Tharp, working with Bruce Heezen, they were given the task of actually drafting profiles of the ocean floor, and this was based on all the data that had been acquired from echo sounding as a ship moved over the oceans. Okay. Now, Marie Tharp was the main person who was assigned this work. Bruce Heezen was actually the lead scientist. He had assigned this work to Marie Tharp. Now, Marie Tharp was an extremely dedicated scientist, and what she did for the first time is, once she was actually looking at the seafloor, she detected that right in the middle of the Atlantic Ocean, there were mountains. In fact, she managed to find out that it was actually a mountain range running all through the middle of the Atlantic Ocean. Not just that, she discovered not just the fact that it was like this, she also discovered that there was a cleft at the top of the ridge. So if this was the seafloor right at the middle of the Atlantic, so this is a cross section, so you had this mountain which was around 2.5 kilometers, right, from the abyssal floor. So the top of the mountain was about 2.5, and at the top you had this little cleft. Now, this cleft that she saw, right, this cut, this was right in the middle of the ridge, right, and she actually assumed that this was something called a rift valley. Now, a rift valley is normally created when two slabs, they move apart and they leave a depression in the middle. That is what a rift valley is. And what Marie Tharp was saying was that the seafloor right at the middle, at the mid-oceanic ridges, it was actually pulling apart, and it was pulling apart, creating a rift valley. She actually went a step further. She was actually saying that it was magma, because it was known by that time that there were volcanoes in some of these mid-oceanic ridges. So these were actually erupting, and this is what was causing the ocean surface to pull apart. Now, what Marie Tharp was saying at that particular time was revolutionary, because she was actually trying to say that the middle of the oceans, which were not passive, they were extremely active entities. Now, she, through the ages, she was given this task, and she did this very, very diligently. Now, this is a map that was prepared by her and was ultimately published by the National Geographic in 1981. So, this is the World Ocean Floor Map, and it gives you a very good idea of what sort of things she talked about. So, you can see that she was actually working in this particular region, and she detected this ridge right in the middle of the Atlantic. So, this is the Mid-Atlantic Ridge. What she did notice is that this Mid-Atlantic Ridge passed right through not just the middle of the North Atlantic, but into the South Atlantic, into the Indian Ocean, and there were ridges all through the Indian Ocean, right into the boundary between the Indian and the Antarctic part, right, and even into the Pacific Ocean. So, these ridges, these underwater mountain chains, were not just unique to the Atlantic Ocean, they were present all over the earth. This is what she managed to show later. So, she demonstrated that it was present in the South Atlantic, the Indian Ocean, the Arabian Sea, the Red Sea and the Gulf of Aden, even here. So, the ridge actually continues here, right, even in this part in the Gulf of Aden, here into the Persian Gulf. There are some markers that people say that it exists in this region as well. Now, this indicated in fact the presence of a global oceanic rift zone. So, Marie Tharp is not always recognized that she was the person who actually discovered these mid-oceanic ridges, what we refer to today as mid-oceanic ridges. Now, although this was such an important discovery, Bruce Heezen, who had actually assigned this work to Marie Tharp, and she was working with Marie Tharp, didn't really believe the interpretation that the seafloor was actually moving apart at the mid-oceanic ridges. Now, the reason he didn't actually accept it at that particular time is that an implication of this theory indirectly, Heezen realized, he was a very intelligent man, he realized that if this happened, it would actually sort of be supporting the now unpopular theory of a continental drift. So, he did not really accept Tharp's interpretation. However, what he did was independently, to find out why these transatlantic cables were breaking, he engaged an assistant. Now, this assistant's name was Howard Foster, and Foster was given the task of mapping all these earthquake epicenters inside the oceans. So, there were a lot of seismometers now set up, and he realized that it was important to find out where these earthquakes were actually occurring. So, what Foster's task was actually to locate these earthquake epicenters. He had to find out where these earthquake epicenters were, and he had to plot them on the epicenters onto the map of the oceans. Now, his task was to plot them exactly on the same scale as Tharp's maps, because Tharp's maps were brilliant maps in terms of the ocean floor topography. They were absolutely brilliant. So, what Heezen realized what a great job Tharp had done, and so independently he asked Foster plot the location of these earthquakes, right, precisely where they were on the ocean floor, where the epicenters were. Now, already Marie Tharp had actually suggested that the earthquake epicenters were actually coinciding with this part. Now, he then noticed when you plot them both on the same scale, Heezen and Tharp actually noticed that the earthquakes all followed the mid-oceanic ridges. Not just that, the epicenters of the earthquakes, they actually fell within the rift valley. Now, once this happened, it meant that the rift valleys were places where stresses were accumulating. And if stresses were accumulating in the rift valley, this implied then that the rift valleys, the middle of the oceans, the mountains in the middle of the oceans, they were actually very active entities. They were not just passive mountains. Now, this is the sort of product, if you plot the earthquake epicenters, right, approximately, it's our approximation of the world map. So, these are the Americas, the new world, this is the old world here, this is Africa, this is India, right, Australia. Now, this is the Atlantic Ocean. Now, as you can see, if you follow this line, so you see the line of earthquake epicenters, you can see that these actually follow this particular part. And if you superpose this on Murray Tharp's map, you would see that this line falls almost exactly, right? It also exactly on the topography that coincides with the mid-oceanic ridges. So, all of these parts, all of the part here, right, the part that goes here goes into the Red Sea and then continues from here, right, right up to about this region here. So, you had this enormous chain, right. In fact, you have more of these a few of these earthquakes also along this part. So, these continue. So, it vanishes from here around here and then reappears this part and comes out here. So, you have these ridges, it forms a global network as Murray Tharp postulated, and you can see that they actually coincide with the earthquake epicenters. So, the topography, this was remarkable, the underwater topography in terms of the mountain ranges, they actually coincide with the locations of the earthquake epicenters. Now, it means then that you had a place where the earthquake epicenters were coinciding. But then if you go back to the map, right, there were some parts, there are no ridges around here, right, there are no ridges in these particular regions. So, if there are no ridges here, but you have this line of epicenters, what does this actually indicate? So, at that particular time, right, when we go into the locations of these major earthquake epicenters, there were, these regions here, right, these regions here. Now, we can use a different color here. Let us see if I have, no, sorry, let us see, I will use a blue one here. Now, that is better. So, the blue ones here, right, that I am drawing. So, you had another line of earthquake epicenters. These were also inside the oceans and they were following, right, a part like here. So, this is all a part that is going through this particular region all along this region here. So, many of these parts here, right, these are parts where you can actually see that there is no relationship of these blue lines. Although these are lines of aligned earthquake epicenters, they have no relationship whatsoever, right, with the mid-oceanic ridges. Indeed, if you actually follow it through, so if you go on across here, so it reappears in this part of the map and all along the western coast of North America, right. So, all along this region here and all along the western coast of South America as well, right. All of these parts, right, you have earthquake epicenters. Now, it is very true, these do not actually coincide, positions of earthquakes. So, what do they coincide with? So, if you go back here, you will see that some of them coincide with the ridges, but the others actually coincide with the ocean trenches. Now, if you go back one step to Murray Tharp's brilliant map, so you will notice that these gashes that exist here, so these gashes part here, these are the ocean trenches, and these ocean trenches were another part, right. These were the other part that was actually coinciding, this was coinciding with the locations of these parts. So, these also fall parallel to the Andaman Islands, for example, parallel to Indonesia. So, all of these regions are ocean trenches, and these ocean trenches also exist along the western coast of South America, and these were the other places where the earthquake epicenters were located. So, it meant then that all these parts that you actually talked of, right, all of these parts that we can see here. So, these regions, even a little bit part that is here, all of these together, they tell you that our earthquake epicenters actually coincided with major topographic features on the ocean floor. They either coincided with the ocean ridges, right, or they coincided with the trenches. So, both of these regions were actually sites of ocean floor topography, and they were actually linked to these earthquake epicenters. Now, if we look at this further now and we do one additional exercise, if you now begin to plot the sites of major volcanoes of Earth, right, and you plot them on the same map, then you will notice something even more interesting. And what was noticed at that time is that if you plot them, of course, most of the major volcanoes, right, you can see that all along the western coast of North America, the sites where the earthquakes were also close to the sites where you had major volcanoes on Earth. So, this happened all through the middle of the ocean. In fact, there will be a lot more spots out here if we had more data right through the end of the ocean. So, we can't actually see most of it because most of it is underwater, but there are numerous volcanoes which are constantly emitting lavas which are erupting onto the ocean floor all along here. So, you have sites of volcanism coinciding with sites of earthquakes, which coincide with major topographic features on the seafloor. These topographic features were ocean rises, the ocean ridges. So, this was something that was realized, that the sites of most major sites of volcanism coincided with the sites of most major earthquakes. So, the sites of major earthquakes then were also the sites of active volcanism on the earth's surface, and these were mostly at the trenches and the mid-oceanic ridges. Now, once this was realized, a connection had been established. Now, this was all taking place in the early 1950s. So, people now began to realize that the seafloor itself, right, the seafloor itself was telling us, giving us a lot of information. It was not as simple and passive as we thought. So, what do we actually take back from the information that we have on the seafloor so far? So, it just means that these long, deep, narrow gases on the ocean floor, these were identified as ocean trenches. They were called ocean trenches by the 1920s. Geophysical surveys of the ocean floor, both during and after the Second World War, they actually gave us a wealth of information on what the ocean floor topography was like. People knew what the topography of the ocean floor was like. Now, there were mountains. Among this, what was noticed is the mountains that occurred more or less in the middle of the world's oceans. Now, although we say it's the middle of the world's oceans, it's middle of the Atlantic Ocean, whereas it's not necessarily in the middle of the Pacific Ocean. It is somewhat in the middle of the Indian Ocean, you can say that. What was important also, that in many of these places, not in all of them, there was a cleft, right, at the peak of the mountain. So, if the mountain was here, so you had a cleft at the top, and this cleft itself coincided with the sites of major earthquake activity. The other places where there was major earthquake activity in the oceans were on the ocean trenches. Now, the ocean trenches were these deep gashes, right. So, there were places where the ocean floor was deeper than the abyssal floor. The ocean rifts were places where the ocean floor was higher than the ocean floor. So, if the ocean floor, you consider it to be the ground level, the ocean ridges were about 2.5 kilometers above that, and the ridges and the ocean trenches themselves would actually be 5 to 6 kilometers below the bottom of the ocean. So, which means that the total depth below mean sea level would be almost 10 to 11 kilometers. And what was finally observed is that it's not just the earthquakes that coincide with the topography of the ocean floor. The major volcanoes on Earth, the major volcanic chains which are active, these also appear to follow rifts and trenches. So, what this was telling us is that the ocean ridges and the ocean trenches, these were the sites. These actually happened to be the sites, right, which were majorly associated with the accumulation of stresses. They were also associated with thermal anomalies. This much was actually realized even by the beginning of the 1950s. What will happen then, what happens subsequently, is what we will discuss in the next class. So, if you look up these references, these are all references which actually deal with many of the things that I have talked about, right. And to look at more at the ocean floor, we will wait until the next one. Thank you for this one.